Topic of this problem is operational amplifiers. And we're going to work with a circuit that is a differential amplifier. The problem is to find the output voltage, V sub out, in terms of the input voltages. So if we look at our circuit that's given, it's an operational amplifier circuit with 4 resistors and 2 input voltages. One input voltage, V sub 1, which is associated with the inverting input of the op-amp, and a second voltage source, which is associated with the non-inverting input of the op-amp. We also have resistors R1, R2, R3, and R4. And V out is measured at the output of the op-amp. So to solve this problem, we have to first understand the basic properties of an op-amp that are important for linear circuits. First of all, we have the symbol for the op-amp. It has its inverting input, its non-inverting input. It has currents associated with both of these inputs, and it has voltages also associated with these 2 inputs. The properties of the ideal op-amp that we use in linear circuits are that the currents flowing into the op-amp are equal to 0, I minus is equal to I plus is equal to 0, and the voltages are equal across whether it's the inverting or the non-inverting input of the op-amp. So these are the properties that we use along with the other tools that we've already used in previous problems to solve these op-amp circuits. So in general, we may use these properties of an op-amp along with nodal analysis, or in some circuits, mesh analysis, to solve for things like the output voltage in terms of the input voltage. So let's see how we solve this problem. The first thing that we notice is that if we're trying to solve the circuit, we need to somehow relate the input voltages to the output voltage. And so we can do that by using the ideal properties of the op-amp and one of our previous tools that we've learned in voltage division across R3 and R4 allows us to find the voltage at the non-inverting input of the op-amp. So our voltage at the non-inverting input of the op-amp using voltage division is equal to V sub 2 times R sub 4 divided by R3 plus R4. So that's our voltage at this point in a circuit. So we know that this voltage is equal to the voltage at the inverting input, which is what we've called node 1 here. And so V plus is equal to V minus, and in terms of the input voltage V sub 2, this is the value for V plus and V minus. Now we can use Kirchhoff's current law to sum the currents into node 1 to find the relationship between the output voltage and the input voltages V1 and V2. So we're going to go to node 1 and we're going to use Kirchhoff's current law. We're going to sum the currents into node 1. So the first current is the current through R1. It's going to be equal to the voltage on one side of the resistor minus that on the other divided by the resistor value. So it's going to be V1 minus V minus divided by R1. And we know what V minus is. It's in terms of V sub 2. And so if we sum the second current through the feedback resistor R sub 2, it's going to be V out minus V sub minus divided by R2. So it's going to be plus V out minus V minus divided by R2. And our third current is the current that's flowing out of the op-amp back into that node 1. And we know that value is 0. I'm going to write it in, but it's one of our basic characteristics of op-amps that we want to make sure that we understand. So now we can write V out in terms of V sub 1 and V sub 2, which is part of our V minus term. And so if we do that, then we end up with a V out which is equal to a rather long expression, R2 divided by R1 times 1 plus R1 divided by R2 plus R4, or times R4 divided by R3 plus R4 times V2 minus R2 over R1 times V1. So it's V2 minus R2 over R1 V1. With these problems, with these differential amplifier circuits like what we've drawn here, many times what people will do is they'll set R1 equal to R3 and R2 equal to R4. Then our equation, which relates V out to V1 and V2, reduces to V out is equal to R2 divided by R1 V2 minus V1. And so what we end up with is an output voltage which is the amplification of the difference between the two input voltages. So we have an input voltage signal from V2 and from V1, and if you look back at the circuit, V2 is tied to the non-inverting terminal. It's not inverted, and V1 is tied to the inverting terminal. It is inverted, and we end up with this amplification factor that we can control by setting our values for R1, R2, R3, and R4 in our circuit. So V out becomes a factor based on R1 and R2 values, and also the difference in the signals between the two input voltages.